Nothing? Yeah, I mean, and Jishan, I mean, your situation, I think, is pretty similar to a lot of the guys here. I mean, they have already studied some machine learning, and therefore, without studying, foundations of data science. And so that's one difficulty that anyone is expected to have if, I mean, he or she is straight away thrown at machine learning. I mean, if you really want to do it, machine learning, and understand how things work. Okay, so I understand that. And my endeavor will be to actually map certain things in machine learning to this particular course. Okay, so I guess that's one thing. And I also clarified some of the other things that I'll be doing and I'll be not doing, right? I mean, so that I hope makes it clear, right? Okay, so let's, let's begin with, asking a question to all of you. Are you familiar with, a thing called computer system performance analysis? I mean, if you are, can you really tell me what do you know about this, or what do you think it is? Even if you have a vague idea. Did you get my question? My question was, are you familiar with computer system performance analysis? Am I audible? No. Okay. All right. Well, so I mean, what it is that, in a, yeah, I mean, Jishan, you're right. I mean, we analyze the different performance systems in a computer. I mean, now, what is a computer system? I mean, a computer system could be an operating system, right? I mean, you have scheduled a task, or you have scheduled multiple tasks. I mean, whether sequentially or parallelly. You have a networking and communication systems, and these are way predated to modern machine learning, where everybody knows that you need to know linear algebra, you need to know probability, you need to know statistics in order to understand machine learning well. But these are like days predated to that craze that we are currently witnessing, right? So I mean, in a computer network system, I mean, what do? We send packets of information and we receive packets of information, right? Okay, and the tasks that are usually undertaken to do such a thing, because that's a very, very important task that forms the backbone of your peer-to-peer communication over the web, etc., etc. I mean, you are pretty much using your hardware systems, right, to do the job. That's your backbone. Now the question is, I mean, in the process of doing so, are you overloading your systems? So that's the first question, right? And if the answer to the first question is yes, right, then the next question is, are there certain tasks, right, which are more responsible for overloading the system compared to certain other tasks? Okay, all right. And if there is a way to find out, let's say I have like 3-4 different factors, right? I mean, contributing to a particular task. Okay, and I also assume that the total workload of the system is because of all these 3 or 4 tasks. So what I can do is, if I want to model the workload of the system, I can model the workload of the system as a linear combination of all 3 or 4 tasks. You understand what a linear combination is, right? So let's say I have task x1, x2, x3, and x4, right? And different timestamps, right? And each one of these tasks can be, stored in a, in an array, right? And you multiply each one of these arrays with certain scalars and take the sum of all of that. So that becomes a weighted or a linear combination, right? And your entire workload is the weighted combination, sum of the weighted combinations of all of this, right? Okay. Now, what we want to know ideally is that out of these 4 tasks, x1, x2, x3, and x4, which one or which ones are more principal towards your system overload compared to the others. Okay, all right. So throughput is one, but then there are other factors as well, like idle time of your system, the delay, the jitter, and lots of other things, right? Okay, so without getting into what exactly is a computer system performance analysis, roughly speaking, this is what it is, right? Now, the question is, how do we figure out which one of these factors are more principal towards contributing to your workload, and which ones are contributing in a much lesser proportion to your cumulative workload? So that seems to be a valid question, right? Okay, but the question is, how do we answer this question? Okay, so let's begin by talking about what is a workload characterization technique. Now, there are several workload characterization techniques. I mean, I hope you can see my screen, and I hope you can see the PDF file, right? Okay. And this is taken from Raj Jain. So there are, one of the things that I have just mentioned to you is to identify the components and select the parameters, right? And there could be multiple ways of characterization of workload, and some of these are statistical, purely statistical, right? I mean, you can take single parameter histogram, you can take 2 parameter histograms, right? And Markov models, you can do some sort of clustering, right? And you can do principal component analysis as well. Okay, so the principal component analysis in essence tells you that if there are a bunch of components present in your system, and if there is a response variable that you are trying to measure the effect of all of these components on, then out of these components, which ones are most important towards measuring the response? Okay, all right. Now, I'm going to skip all of that because these are not relevant to what we want to talk about, right? I mean, so let's jump straight away into what is principal component analysis. Okay, once I finish this part, I'm going to tell you why I started talking about principal component analysis before even giving you any notions of what are the standard concepts in linear algebra. Okay, so as I said, we use a weighted sum of parameters. Okay, and each parameter has some components because you are storing them as an array, right? Okay, so therefore, what will happen is each yj is supposed to be providing the maximum discrimination among the components. Okay, all right, and each yj is called a principal factor. So once you compute the principal factors and basically compute the contribution of the principal factors to your final response variable, you order them out and you see which ones are most dominant, and you identify those as the principal factors. Okay, and this dominance is usually measured by the amount of variance it can actually affect towards the final response variable. Okay, all right. So as I said, I mean, the y's, all the response variables, I mean, all the principal factors are nothing but linear combinations of x's. Okay, all right. Now, the expectation is that the y's will form an orthogonal set. Forget about, what I want you to do is during this particular presentation is that whenever you hear a particular term that you are not familiar with, like for example, I'm expecting that orthogonality is something you are not really familiar with. Okay, all right. I mean, it means perpendicular, but that's an oversimplification. So you note it down immediately. Okay, so the expectation is that the principal factors form an orthogonal set. Okay, and why? That's because, I mean, why is that expectation? Is because if you do this right, then no principal factor can be sort of dependent on another principal factor. So you should not be able to express one principal factor as a linear combination of the other principal factors. So you would want sort of these principal factors to be as independent of each other as possible. Okay, so orthogonality will give you that. So what Raj Jain says is that the orthogonality, if the principal factors form an orthogonal set, this is equivalent to stating that these principal factors are uncorrelated to each other statistically. Okay, all right, and then you form an ordered set of all of these principal factors. Okay, so far so good. Okay, now the way we do it is that we find a correlation matrix. So now I would want you to think of a particular problem, that number of packets sent and number of packets received. Now typically, let me ask you another question at this point of time. Are you guys familiar with distributions, probability distributions?
Yes, sir.
You are, right? So you are familiar with geometric distributions, Bernoulli, binomials, so on and so forth, right?
Sir, we need to recall it, sir. So we forgot it.
Okay. All right. Okay. All right. Now I'll give you an example purely from this context of sending packets and receiving packets, right? So let's say you have a communication channel, right? Let's say you have a communication channel, and you are sending packets, assuming that there would be a number of failures. You would expect a number of failures before the packet is successfully received at the other end. Okay, right? So, and then what you really do is there are two probabilities here. One is that the probability of success, which is when you receive a packet successfully at the receiver end. And therefore, 1 minus p is the probability of failure. Now, this is a particular communication channel where you would expect a lot of failures to happen, right? So you send a packet and you did not receive it, right? Okay, so it's 1 minus p. You send the packet again, and still on the second attempt, the packet is not received, and on the third attempt, and you go on until the packet is received successfully, right? So if you have n number of tries in a sequence, then you are looking at a probability 1 minus p raised to the power n minus 1 times p, isn't it? Where p is the probability of success. The moment you receive the packet successfully, and these two events are independent of each other, right? Okay, so therefore you take the product. So this particular distribution, so this particular probability structure is governed by a distribution known as a geometric distribution. So what really happens is, if you let such a communication system go on, right, then naturally on that particular channel, you are actually imposing a lot of load, because each and every time you send a packet, right, I mean, there is some workload that the system has to go through. And if your number of failures are much more than your number of successes, right, okay, then obviously your system will be loaded and you're without much benefit, right? So there could be, from geometric distribution, we can also think of something else. So let's say there are n number of attempts, right, and out of which you have achieved k number of successes, right? Okay, so what will happen is your p is the probability of success and 1 minus p is the probability of failure, right? So a derivative of a geometric distribution is this, that your p to the power k, because you have k number of successes, and therefore you have n minus k number of failures, right? So you have p to the power k times 1 minus p to the power n minus k. These two things combined, actually multiplied with each other because these events are independent, form the crux of your another distribution, which is derived from the geometric distribution. Now you can shuffle this, right? So in how many ways you can shuffle this? You can shuffle these in n choose k ways. So the way this distribution looks like is n choose k, p to the power k, 1 minus p to the power n minus k. This has a direct ramification in binary classification problems, where the probability of a sample belonging to one class can be thought of as p, and probability of that sample not belonging to other class is 1 minus p. Okay, all right. However, let's come back to this communication channel problem, right? So therefore, what you should be able to appreciate is the following, that this is a valid problem to take stock of. I mean, number of channel packets sent and number of packets received. And if we have some data, I mean, can we figure out a way to see or ascertain or quantify which one of these two components is a principal factor towards your workload estimation? Okay, so that's the problem statement. How we solve it is now what we are going to talk about. So what we do is, typically we find the correlation matrix between the vectors which store the number of packets sent, and the vectors which store the number of packets received. Now, once again, I have introduced another term that you probably are not familiar with, vectors. So the first term is orthogonality. The second term is vectors. Okay, all right. And now I'm also going to introduce a bunch of things, at least a couple of things, which you probably have heard of, but you don't really know what these are. Which is, I mean, once you formulate a correlation matrix, right? I mean, you could compute the eigenvalues of the matrix, right, and sort them in the ascending order. You can, for each one of these eigenvalues, you can compute the corresponding eigenvectors. And these eigenvectors are supposed to give you the required loadings corresponding to each one of these principal factors. Okay, all right. Now, this is the data that we have. Okay, all right. So we have the variables represented as XS and XR. XS denotes the number of packets sent, and XR denotes the number of packets received. Okay, and we have 18 such samples. And if you look carefully at the data, you would see that there are large variations in the data set. Right, there are pretty large variations in the data set. So what we typically do is, I mean, of course, if you plot the histogram of these 18 data points, you will see that the histogram for both number of packets sent and number of packets received follow an approximate Gaussian distribution. Okay, so what you can do, you can normalize it. How do you normalize it? You normalize it by subtracting the mean from each one of these samples and dividing it by the standard deviation. Okay, all right. And those things are computed in the table itself. And so in the next column, you will see the normalized variables, right? Okay, all right. And if you have done the principal factors correctly, and don't worry about the last column, we'll come back to this later, right? You will see that the average of the principal factors would always be 0. Okay, all right. So that you would measure how each one of these principal factors, what is the statistical deviation of each one of the, or statistical spread of each one of these principal factors around that mean. Okay, all right. So, I mean, we compute the mean, we compute the standard deviation, forget about all of that. These are pretty standard, right? And our main interest is to get to the matrix. Okay, all right. And we do that, we normalize the variables. I have already explained this. And we compute the correlation matrix. It's a standard Pearson correlation formulation that we do. And this matrix is a 2 by 2 matrix, has to be, right? Because your first row would be the XS, which is the number of packets sent as a variable, and the second row would be XR, which is number of packets received. First column is XS, and the second column is XR, right? So basically, what is the correlation between XS and itself? 1, right? So therefore, what this correlation, the Pearson correlation formula helps us establish is to find the components which are not on the principal diagonal of the matrix. I hope you know what a principal diagonal is, right? Okay. Okay, now you look at this matrix carefully for a moment, okay? So the elements of this matrix are, it's a 2 by 2. Elements of this matrix are 1, 0.916, 0.916, and 1. Do you see anything special about this matrix? Simply by visual inspection. Excellent, symmetric. Shrestha, I will use a whiteboard. I actually have a whiteboard, but my webcam is not powerful enough. So I have ordered a webcam, it's on the way. Okay, all right. And actually last semester I taught a WILP class, and there we did not have to face this problem as we were using the studio. Okay, so just bear with me. Okay, so I'm not proving anything now. So when I start proving things, I'll definitely use a whiteboard. Yes, so you're right. So it's a symmetric matrix. Very good. Okay, it's a symmetric matrix. How do you know it's symmetric? Because if you take the transpose of this matrix, I mean, nothing will change, right? Okay. So note this down. This is another important aspect of this correlation matrix, that it is symmetric. Okay, and a symmetric matrix or an equivalent transformation of that has some very important properties which help us figure out or help us establish our earlier assertion, what was our first assertion when we talked about principal component analysis? The first point that I asked you to note down was the assertion that the principal components will, or principal factors will form an orthogonal set. Okay, all right, if you recall. Okay, so now, I mean, you really don't have to know at this point of time how we compute the eigenvalues, okay, because I'm going to come back to all of that later. But for now, I mean, if we indeed compute the eigenvalue and by solving the characteristic equation, we will see that the eigenvalues of this matrix are 1.916 and 0.084. Now, the question is, once again, when you look at these eigenvalues, what do you see? That will be the fourth point to note. What do you see when you look at these eigenvalues? The eigenvalues are 1.916 and 0.084. That is good, but the real obvious thing. Okay, all right, very good. You are actually, observing things that I have not observed. They do add 2, but that's not really, the average is 1. All right, all of this is correct, but I'm really looking for the obvious answer. It's 1.916 and 0.084. Oh, Mohit says unstable. So I am guessing you know something about the spectral analysis of eigenvalues and eigenvectors. But let's not get into that now. And Aman, you actually asked a question that can XR exceed XS. I mean, the number of received packets can be greater than the number of sent ones. That usually does not happen because there is always some latency and loss in communication channels. So that's the assumption. So I mean, you are not telling me the obvious one. I'll repeat. 1.916, 0.084. No? Is it so difficult a question? Okay, yes, both are positive. 1.916 and 0.084. Come on. They're different from each other, aren't they? Right? I mean, 1.916 is not equal to 0.084, right? Okay, why do I ask this question? Because, I mean, your characteristic equation, I mean, in this particular case, because it's a 2x2 matrix, I mean, we are actually solving a quadratic equation, right? I mean, there is no guarantee that the quadratic equations will always give you different roots, right? I mean, for example, if you're solving x minus 1 whole square equal to 0, that's also a quadratic equation and could very well be a characteristic equation as well. Then what are the roots of that equation? 1 and 1. Okay, so assuming that is to be a characteristic equation, the eigenvalues would actually be 1 and 1. So they could be real and equal. But in this particular case, the eigenvalues are real and different from each other. So that is the point number 5 that you need to note down. So what did we say? We did say a bunch of things. We basically actually posted a bunch of claims. The first claim was that the principal factors form an orthonormal set. Okay, all right. And then we saw that there are vectors and matrices involved. We saw that we have to do some eigenvalue, eigenvector computation of the matrix. What we observed was that the correlation matrix is a real and symmetric matrix. Why I say real? Because the entries in the matrix are all real. Okay. And the next thing now that we observe is that the eigenvalues are real and different. Okay, so these two statements, I mean, please note point number 6, that is there a relation between the correlation matrix being real and symmetric and the corresponding eigenvalues being real and different from each other? Did you get my Question? I mean, did you get what I wanted to write you? I hope you did, right? I'll repeat. There is an assertion, there's an observation that the correlation matrix is real and symmetric. There is another observation that the corresponding eigenvalues are real and different from each other. Is there some relation between the two? Okay, please note this down. Okay. All right. I bet there is a relation, but we'll see. Okay, so let's move on. And I'll just skip this because I mean this is not really important. I mean the how you compute the principal components are not important. Okay. Now what the principal components are, these are the eigenvectors corresponding to the eigenvalues. So you could have two principal components here, right? Okay. And then what you do is, I mean, don't worry about these computations, okay? But just look at Q1 and Q2. These are the two corresponding eigenvectors to the eigenvalues that we computed before. Lambda 1, which is 1.916, and lambda 2, which is 0.084. Right? Once again, I would ask you to observe something. Look at Q1 is a column vector. Q2 is also a column vector, right? Are you familiar with dot products? I think that's something that you have learned in school, right? Okay. Now, can you do me a favor and take the dot product of Q1 and Q2 and tell me what it is? Yes, excellent, right? Okay, so I mean in the subsequent lectures, I'm not going to use the word dot product, but I'm going to use the word inner product. So note these down as well, okay? So somewhere down the line, when we are talking about principal component analysis, there is another keyword that pops up, which is inner products of vectors. Okay, all right. Now, the inner product of two vectors are, in this particular case, inner product or dot product of the two vectors is equal to 0. What does it mean? Yes, okay. Well, it means that the vectors are perpendicular to each other, right? I mean, because, I mean, from a very simple point of view, if you look at the dot product formula, the dot product of two vectors is nothing but the product of the length of each one of the vectors times cosine of the angle between them, right? If you remember the formula. Now, the angle between the two vectors, if it's 90, then cosine of 90 degree, we know that it's equal to 0. So therefore, the dot product is also 0, right? Okay. Now, yes, orthogonal components. Now, the point is this once again related to something that we have already observed before? Is it related to the nature of the eigenvalues? Okay. So once again, I'll try to, link the threads that we observe that the matrix is real and symmetric. We observe that the corresponding eigenvalues are real and distinct. And now we observe that the corresponding eigenvectors are orthogonal to each other. Are these related? Okay, so that will be the point number 6. Okay, all right. So in each class, I would want you to note down these takeaways. Okay, so that you can collect back when you read the material on your own, right? Okay. So, I mean, as I said, I'm not interested in computing, knowing how these things are exactly computed. So whatever formulation it's being used, okay, the idea is that if you use that, you will eventually get this outcome, which is that the first factor, which is nothing but the number of packets sent variable, and the second factor, which is nothing but the number of packets received variable. So if you follow the formulas of principal component analysis, you will be able to see that the first factor explains 95.7% of the variation. Now you look at this image here, okay? The first factor is along the horizontal axis, and you can see there is maximum discrimination. It's able to explain the variance of the response variable, right? Around that line 0. What is that line 0? That line is nothing but the mean. If you recall from the table, we computed the mean of the principal factors, right? Okay, for both of these, for both XR and XS, the mean was at 0, right? So now you look in the vertical direction, is the principal factor 2, which is nothing but the number of packets received, right? So around that point, you know, you will see much lesser variation. Okay, all right. So from this, it is sort of clear that the number of packets sent is much more important towards contributing to the workload of your system compared to number of packets received. Okay, all right. So now that we know this, we can go back to the system and design more efficient ways of packet transmission so that there is not much loss. Okay, so there is lossless transmission. There are different things that computer networks people have devised over the years, over the decades, right? I'm not going to talk about those. But the takeaway of doing such a thing in principal component analysis for a problem that we studied in computer system performance analysis is this. Okay, what lies beneath are that this particular method is fundamentally driven by concepts in linear algebra. Okay, all right. So I hope the picture is clear to you now. No, Aman, because I mean, I think, let's say you have bunch of factors. In this particular example, there are only two factors, right? I mean, number of packets sent and number of packets received. If you have a bunch of factors, all of these factors, there is a formula based on which we can compute the contribution of each one of these factors with respect to the response variable. Okay, that when I get back to principal component analysis again, okay, again I'll come back to this after we have gone through the essential concepts in linear algebra. I'll explain how to compute the contribution of each one of these factors. But in this particular example, you had only two factors, y1 and y2, and by a simple empirical demonstration, we have seen that these y1 and y2 form an orthonormal set because their dot product or inner product is 0. If you expand this to a bunch of principal factors, then the pairwise dot product of all of those principal factors would also turn out to be 0. Okay, all right. Okay, so this is what it is. So therefore, I mean, you know, there are a bunch of things. That we actually just talked about. I mean, we haven't really talked about. We just mentioned that these are the things in linear algebra or foundations in data science that you need to know and understand. Okay, but I wanted you to appreciate the concepts by virtue of going through an example. Okay, all right. So, okay, the load percentage is the variance, right? So if it's 97.3% because of the number of packets sent, so that will explain maximum variance along that direction. Okay, now, so you have that horizontal line, okay, and you will see a bunch of data points spread across that horizontal line, right? So that will actually explain that this is the maximum discrimination to the response variable because of principal component 1. Okay. Similarly, along the vertical direction. Okay. All right. So the load percentage is precisely calculated using a formula. And as I said, when I was talking about it, I said that I'm not interested at this point of time to tell you what that formula is because that's not important. Okay. All right. Okay. So we did talk about a bunch of things, right? I mean, we did mention vectors. We mentioned matrices, right? We also mentioned linear transformation one time, right? We mentioned inner products. We mentioned eigenvalues, eigenvectors, orthogonal sets, and so on and so forth, right? Yes, I mean, that's a very good question, right? I mean, exactly. I mean, see, if the correlation matrix, so Sanjay had asked a question that what's the link between the correlation matrix being real and symmetric and the eigenvalues being real and distinct, okay? So there is a result that I will prove that if any matrix is real and symmetric, the eigenvalues are real and distinct, okay? That's a theorem that we will prove. And I will also prove that if the eigenvalues are real and distinct, the corresponding eigenvectors are orthogonal to each other. So that it's true each and every time. You don't have to empirically calculate and find out, like the example that we did here. And also I will prove that if the set of vectors are orthogonal to each other, they are also linearly independent of each other. Okay. Well, I is symmetric, isn't it? 1, 0, 0, 1. No, but that is, no, sorry, Sanjay, but that's just an aberration. I mean, that is not, I mean, if the eigenvalues, it's not an if and only if relation. So if the eigenvalues are real and equal, that does not mean that the matrix will have to be real and symmetric. But if a matrix is real and symmetric, the corresponding eigenvalues would be real and different. Okay, all right. Yes, we discussed the scalar multiples of y. Okay. I mean, unless we want to build two other projection spaces, which I'm going to talk about later, right? But these are all just one-way relations. So if a matrix is real and symmetric, the corresponding eigenvalues are real and different. The other way around might not be true. Okay. All right. Okay. So now what I'm going to do now. So I mean, I talked about principal component analysis for whatever it's worth, right? So let's now get to something else. Okay. Okay. So this presentation also, this PowerPoint presentation also, I have shared in the class folder. And in this class folder, you will see a few lectures on linear algebra, as well as a bunch of linear algebra notes that I have curated over time. Okay. There are other things as well that you could have access to. Okay. Okay, so we have already answered the first question, haven't we? I mean, why do I care about linear algebra? I mean, why do I need to talk about or study linear algebra, right? And then what are the key terms? What are the interpretations of some of the things that we learn in linear algebra? I have already given you an example, principal component analysis. We will also talk about another very important example, which is singular value decomposition, and how singular value decomposition is related to principal component analysis. We will also talk about a very important problem that is a pretty old method. It's called a least square estimation, right? I mean, how that is related to the concepts of linear algebra. Okay. We will talk about some applications in machine learning, right? Okay. And this is what is the most important. I mean, as I said in the beginning of the lecture, I do not like treatment in books which are dependent on computing determinants of matrices to know about your matrix properties. Because if your matrix is of small size, your determinants are easily computable. If it's large, the complexity of a determinant operation is of the order of n squared, right? So if your n is 10,000, if you're looking at a 10,000 by 10,000 matrix, you're actually looking at a pretty expensive operation each and every time. Okay, all right. So instead of computing the determinants of matrices, can we still figure out whether there are useful properties of matrices and corresponding linear transformations that we derive? It is in this context that there are two excellent books by Sheldon Axler. One I have already shared with you, okay, and the other one is Down with Determinants. This I cannot find online, but the one that I shared with you, with the name of the book is Linear Algebra Done Right, should actually serve the purpose. Okay. Okay. So what are some of the interesting popular problems that directly use concepts in linear algebra? Okay. One is matching similarity problems. Now, what is matching similarity problem? An example in matching similarity problem can be a matrimonial site or a dating site, okay, where one partner is matched with another partner. Now, how do you do that? Okay, you can compute the, I mean, you can store, so you need a bunch of features, right? I mean, what kind of movies you like, what kind of food you like, what kind of music you like, okay? I mean, of course, there are certain other things like age group. I mean, what do you expect? I mean, what are the other things that you do? What are your hobbies and so on and so forth, right? And each one of these features, I mean, can be stored in an array. So let's say there is a partner X1 and the partner X2 is once again the same features, but will have different values, right? Okay. Now, I mean, ideally, would you really like your x1 right now where x1 is, and right now where x2 is, right? So x1 is one partner and x2 is another partner. I mean, would you really like the current alignment of x1 and x2? No, the video is not frozen. Would you like the current alignment of x1 and x2? So currently, what they are oriented at right angles to each other, right? Usually, that's not the way these matching sites work, right? So if one partner is orthogonal to another partner, the match is sort of very, very low. Okay, so naturally, it's not a good match, correct? Now, how do you figure this out? You figure this out by simply, you do not really draw pictures all the time, right? So you simply figure out by using or computing the inner product between the two vectors. And computation of inner product is really a cheap operation. Okay, you know dot product, right? You have two vectors, 1, 1, and 1 minus 1. How do you compute the dot product or inner product of the two? 1 times 1 plus 1 times minus 1. It's just, pairwise multiplication. It's really a cheap operation, right? So by simply computing the inner product, you could actually match partner x1 with partner x2. Okay, if the dot product value is not 0, right? If the dot product value is, let's say, close to 1, what do you say? We say that the two vectors or the two partners x1 and x2 are sort of really very, very compatible because they're close in terms of the kind of things that they like. Of course, you have to sort of figure out your feature sets, right? Yes, good match. Okay, so that's one direct application of linear algebra, right? I mean, pretty simple. I mean, you can also simply compute the Euclidean distance between the two feature vectors and see how close or how distant they are, right? Okay. There are forecasting classification problems which use the concepts of linear algebra. Okay, I mean, in this context, we will talk about regression problems a little bit. Okay, all right. Okay, just the setting of the regression problem, right? We will also talk about, usually in a linear regression problem, I don't know if you're familiar with this, we usually, there is an error function, right? Which is, I mean, you are predicting something and your predicted level may not be the same as the original level, or your forecasted value may not be the same as the exact value, right? So you would like to know the difference between your forecasted value and the exact value. And because the alignment of these values in spatial geometry could be anywhere, one standard trick is to take the difference, square the difference of all the data points, take the sum of it, right? Okay, and then minimize this. Okay, so if the minimization is really a good minimization, we would say that the predicted values are close to the exact values. And this is actually a least square problem that we would address after we talk about all the important concepts in linear algebra. Okay. Then there are decision boundaries in classification. Once again, just go to this picture. This is really a two-class problem where you would want to discriminate objects from one class from objects of the another class in such a way that there is a significant boundary between the two. So you can also do it by trying to draw a straight line between the two, but then the problem would be there could be certain objects, okay, from both classes which could come very, very close to just one line. And that will give rise to a region of confusion. Which class level should you assign this particular object to? So in order to get rid of that confusion, there are two other parallel vectors that are drawn so that there is a width or a margin that is kept between the objects of the two classes, okay, to reduce misclassification. Now, how do you do it? One simple way is that assume that the blue ones, one of the blue guys, fall into the region where the green guys are. If that's the case, what are you going to do? You actually can do a projection. You project it at least. How much? You project it at least of the length of that width or the margin. Now, how do you project it? You project it using inner products. So here is another concept that we will use to solve problems like this is a projection. And a projection involves inner product. Okay, so once again, linear algebra. Okay, then there is this thing called matrix exponentiation. I mean, if I give you a large matrix, right, and I ask you to find the 23,000th power of that matrix, I mean, you would be at a loss, right? I mean, you could give it to a computer, but even for a computer, it will be an expensive computation. Now, are there ways to simplify this computation? The answer is yes. There are ways to simplify this computation if that matrix exhibits certain special properties. Okay, and one of these special properties is a symmetric property. If the matrix is a symmetric matrix, then it can be broken down into a bunch of smaller and more nicer matrices, and then this exponentiation operation, which is nothing but multiply the same matrix a number of times, becomes really, really easy. This is once again done using some concepts in linear algebra. And then the most classical example is, I mean, where linear algebra actually started like 200 years back, is that I have a system of equations. I want to solve this system of equations. Okay, all right. And then dimensionality reduction, which is nothing but PCA that we talked about. Okay, all right. So I think, I mean, we have 5 minutes, right? Good. Okay, I think we have 5 minutes. So at this point of time, let me go to the classroom. And I think I have addressed all of your questions, right? Do you have any other question that you would want to ask? Because we are getting to the end of the class. Okay, let me ask you a question. So is it, I mean, do you realize the importance of doing linear algebra? Not only from the point of view of machine learning, but in general. Do you realize why we should be doing what we are doing? Yes, yes, okay, all right, yes. Yeah. I mean, as I said, I mean, guys, I mean, I can see that most of you are just fascinated to machine learning, okay? I mean, categorization objects in real life. Yes, I mean, that's classification, right? Okay, but even other than classification, there have been other problems which have existed way before, machine learning came in, right? Pattern recognition and machine learning is basically started in 1960s, if you know the history. But computing existed before that, right? I mean, so that's the reason I gave you an example from a computer system performance analysis perspective. And I also gave you a bunch of examples which are directly or indirectly linked to machine learning, but independently, all of those problems stand on their own ground, right? Okay. But yes, a lot of real life applications, but do you also realize what sort of real life applications linear algebra is relevant in? I gave you a bunch of examples, right? Okay, so what I would like you to do now is, I don't know, Jishan, what you mean by customization, but I mean, you can probably send me an email and we can, discuss, right? Okay, but so hopefully the answer is yes, that you have understood. Yeah. So that's basically, in order to suggest products to a customer, I mean, the approach that most people take in retail business is clustering. Okay, and while you do clustering, you actually use some measures of distances. I mean, people typically do not use Euclidean distances; they use other kind of distances. But we'll talk about that as well. But it's sort of relevant. Yes. Okay, so I'll just repeat. The 24th and 26th August, these two classes will have to be at 6 p.m. because I can't take the class at the scheduled time. Okay, I have already made an announcement and moved that announcement to the top of the classroom board. 666, because somebody told me that there are classes at 5 p.m. So that's why I said 6. Okay. All right. So any other question for me? I understand some of you have conflicts, but I can't. I mean. So will 7 p.m. work? Yeah, the lecture videos will be shared. I'm just recording. Okay. 7 is okay, right? Okay. So what I'll do is I'll just, edit that, announcement. Okay. So all right, guys. Okay. I'll just. I have not used, I'm not using Quanta, Sanjay. I have just used Google Classroom. And if you share your email ID with me, I'll add you to the Google Classroom. That's not a problem. No. Send me an email. Don't share here because I'm going to stop presenting and leave this. Okay? Just email me. All right, guys. Okay?